Hello everyone. The question on everyone's mind: have we found life on Mars or not? This week NASA announced an extraordinary discovery made by the Perseverance rover, the detection of a mineral that, on Earth, is closely associated with microbial activity. But does that really mean we've discovered Martian life? The answer is far more complex and fascinating than a simple yes or no. In this video, we'll explore this revolutionary discovery and break down exactly where we stand in the search for life on Mars. First, it is important to temporally contextualize this discovery. Although the announcement was made this week through a publication in the prestigious journal Nature, the observations actually took place in July 2024. In planetary science, especially when dealing with possible biosignatures, the time between observation and publication can be extensive. Every detail needs to be meticulously verified, every alternative interpretation needs to be considered, and every piece of evidence needs to be examined by multiple independent experts. The Perseverance rover was exploring a fascinating region called Shayava Falls, located within the Jezero crater, the landing site carefully selected precisely for its astrobiological potential. Jezero crater is not just a random depression on the Martian surface. Billions of years ago, it was home to a deep lake, fed by a complex river system. One of the most notable features of the Jezero crater is the Neretva Vallis, a deeply carved valley that cuts through the crater rim. This valley did not form gradually through slow geological processes. It was catastrophically excavated by enormous volumes of rushing water, enough water to transport car-sized boulders and deposit a massive delta inside the crater. This delta, now petrified and dry for billions of years, is precisely the kind of environment where, if microbial life existed on ancient Mars, we would expect to find preserved evidence. Deltas on Earth are notoriously rich in fossils and organic matter because running water transports fine sediments and organic materials, depositing them in ordered layers within low-energy environments. Within this delta system, Perseverance identified a specific rock formation nicknamed Bright Angel, an outcrop that stood out for its unusual composition and texture. It was in this formation that the extraordinary discovery was made. The Perseverance rover is essentially a state-of-the-art mobile laboratory, equipped with instruments that represent decades of technological advancement beyond previous missions. Two instruments were crucial for this specific discovery. The first is Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals. The name is obviously a reference to the detective Sherlock Holmes, but the acronym also precisely describes its capabilities. Sherlock uses Raman spectroscopy and ultraviolet fluorescence to detect organic compounds and map mineralogy on a microscopic scale. When we illuminate materials with ultraviolet light, organic molecules often fluoresce. They emit light at characteristic wavelengths. Different classes of organic compounds produce distinct spectral signatures. Sherlock can detect extremely low concentrations of organic material and determine its spatial distribution within the rock. The second crucial instrument is Pixel, planetary instrument for X-ray lithochemistry. This device essentially takes X-rays of the rocks, but in a much more sophisticated way than medical radiography. When high-energy X-rays hit a rock surface, they cause the emission of X-ray fluorescence characteristic of each element present. Pixel can create detailed elemental maps showing the distribution of iron, calcium, magnesium, sulfur, and other elements on a sub-millimeter scale. When Perseverance drilled the Bright Angel rock and examined the freshly exposed material, something remarkable appeared in the images. Small circular patches with a concentric structure, cores of one composition surrounded by rings of a different composition. The mission geologists immediately nicknamed them leopard spots due to the visual resemblance to the great cat's coat pattern. These spots are not merely visual curiosities, they represent something geologically significant: preserved chemical reaction fronts within the rock. At some point in the rock's history, fluids percolated through it, triggering chemical reactions that transformed original minerals into new minerals. The leopard spots are literally chemical fossils, preserved records of ancient geochemical processes. When Sherlock spectrally analyzed these leopard spots, it detected the so-called G-band or D-band, a spectral peak around 1500 centimeters to 1 in the Raman spectrum. This band is diagnostic of the presence of organic compounds, carbon-based molecules with carbon-hydrogen bonds. It is crucial to emphasize here, organic does not mean biological. Organic in chemistry simply means containing carbon in specific bonds. Organic compounds can be produced by purely geological processes, reactions between volcanic gases, hydrothermal alteration of minerals, or catalytic synthesis on mineral surfaces. Meteorites that have never hosted life are full of complex organic compounds, but the presence of organic compounds is necessary, though not sufficient for life. Detecting them in a geological context favorable to the preservation of biosignatures is encouraging. The pixel elemental analysis revealed something even more intriguing. The cores of the leopard spots contained a mineral called greigite, an iron sulfide with the chemical formula Fe3S4. Greigite is magnetically active and structurally related to magnetite, but with sulfur replacing some oxygen atoms. Why is greigite significant? On Earth, this mineral forms predominantly in sediments, where sulfate-reducing bacteria are active. These microorganisms metabolize sulfate dissolved in water, generating sulfide as a waste product. This sulfide then reacts with iron to precipitate greigite and related minerals. Indeed, if you search for greigite in Earth's scientific literature, you will repeatedly encounter the phrase, associated with microbial activity. The mineral is considered a possible biosignature, not definitive proof of life, but an indicator that, in the appropriate context, suggests biological processes. But, and this is a huge and crucial but, greigite can also form through purely geochemical processes. Under specific conditions of temperature, pressure, pH, and chemical concentrations, inorganic reactions can produce greigite without any biological involvement. Here we arrive at the crux of the matter. How do we determine if the Martian greigite is of biological or geological origin? Level 1. We detect a possible signal. Yes, greigite and organic compounds were detected. Level 2. We eliminate terrestrial contamination. Perseverance was meticulously sterilized. Contamination is extremely unlikely. Level 3. We confirm the environment was habitable. Ancient Jezero clearly had liquid water, necessary chemicals and energy. Level 4. We rule out non-biological processes. Here we are stuck. We cannot definitively rule out a geochemical origin for the greigite. To progress beyond Level 4, we need analyses much more detailed than any Martian rover can perform. We need to examine specific isotopes, look for molecular chirality, characterize microtextures at the nanometer scale, and perform dozens of different chemical and mineralogical tests. These capabilities exist only in sophisticated terrestrial laboratories. This brings us to the most frustrating problem in this entire story. We need to bring the rocks from Mars to Earth, but the mission planned to do exactly that is currently cancelled or significantly stalled. The Mars Sample Return Mission, MSR, was one of NASA's most ambitious projects, a multi-billion-dollar international effort involving multiple launches, a fetch rover on Mars, a Martian ascent rocket, a rendezvous orbiter, and finally a re-entry capsule bringing the precious samples back to Earth. Perseverance has already collected and stored dozens of carefully selected samples, including material from the leopard spots. But due to budgetary constraints and technical challenges, the original mission architecture was deemed unsustainable. NASA paused the project and is re-evaluating simpler, more cost-effective options. Meanwhile, China is accelerating its own Mars Sample Return Mission, Tianwen-3, which is currently planned for launch around 2028-2030. The situation is simultaneously exciting and frustrating. We potentially have in our hands the most compelling biosignature yet found on Mars, but we cannot properly analyze it with the technology available on the Red Planet. It is like finding a treasure, locked in a safe without having the key. It is absolutely crucial to maintain appropriate scientific perspective. The Perseverance team has been exemplarily cautious in their communication. They did not claim to have discovered life. They claimed to have discovered features consistent with possible ancient biological activity, while explicitly acknowledging that purely geological explanations remain viable. This caution is not pessimism or lack of enthusiasm. It is appropriate scientific rigor. The history of science is filled with discoveries of extraterrestrial life that were subsequently proven to be mistaken. The Martian meteorite ALH8T4001, announced in 1996 as possibly containing microbial fossils, is now generally considered to lack unequivocally biological features. Lessons have been learned about the importance of healthy skepticism and rigorous standards of evidence. So, did we find life on Mars? The honest answer is, we do not know yet. But we found something extraordinary, perhaps the most promising clue to date that life may have existed on the ancient red planet. Compared to other possible biosignatures in the solar system, Enceladus's plumes, Europa's subsurface ocean, Mars offers a crucial advantage: proximity and accessibility. We already have sophisticated rovers on the surface, we have already collected samples. The technology to bring them back to Earth exists, even if the specific implementation remains uncertain. This Perseverance discovery represents exactly the kind of incremental yet significant progress that characterizes good planetary science. Each mission builds upon the last, each discovery raises new questions, and each answer brings us closer to understanding if we are alone in the universe. The journey continues, and the rocks waiting on Mars may eventually reveal their secrets.